Welcome back to Quick Soil Mechanics Lessons with Brian. Continuing with lessons in pore pressure. Today, flow nets, or as I like to think of them, beautiful squares. So, soil mechanics is a lot about effective stress. Effective stress is a very important principle in soil mechanics, and pore pressure is key to that. So, good understanding of pore pressure is critical to the development of a geotechnical engineer. So let's look at flow through a homogeneous dam, and this one will have an impermeable base, and the soil will have isotropic properties. So let's just start with our model. Let's say it's inside of a tank. Here's our dam. It's homogeneous fill, like I said. It's isotropic, so the properties are the same in all directions. We'll fill that up with water, and we'll put a little bit of dye at a couple of different locations in here, and let's see what happens to that dye when we start letting it drip into the dam with the water flowing through it. So the upper one looks like this, middle one goes something like that, and the bottom one goes something like this. Well, what are those things? Well, those are flow lines. Those are called flow lines. It kind of makes sense, doesn't it? And there's also another thing in there. That's the phreatic surface. Well, we hadn't drawn the phreatic surface in there. The phreatic surface is also a flow line. And we'll see this zone here has seepage coming out on the face of the dam. And it's just a physical law that if you have a situation like this, you'll have seepage. It doesn't matter how tall the dam is or what the slope of that downstream slope is, you'll have seepage. And a guy named Arthur Casagrande, many years ago, 1937, made this publication, which is a really good publication, still holds valid today. And in there, he had several different solutions. One of them is for where seepage comes out on a homogeneous isotropic earth dam. So his equations tell you that you will have seepage there. And that's why we usually include some type of internal drain in there. Well, inside that book, he's got this interesting illustration. This is the same thing that I just showed you, some dye trace going through a dam. And here it says with an overhanging discharge slope. So that would be a drain. So it's seeping into a drain. Those are flow lines that are illustrated with dye going through the fill. So let's get back to our dam model. So we've got these flow lines in the phreatic surface. So again, this homogeneous dam, impermeable base, isotropic properties. Now it's not a tailings dam, but tailings dam is a little bit more complicated, but it's the same kind of principles. So let's clean this up just a little bit, and let's put in lines that are in basically 90-degree angles to those things. You'll notice that they're all approximately square, or as square as you can get with some of those angles in there. And all the angles are essentially at 90 degrees. And when they're not, it's just my inability to scribble on a computer that led them not to be 90 degrees. Well, those new lines that I drew in there are called equipotential lines. And here we see a definition of equipotential lines. They're lines where all the points have the same energy. They intersect flow lines at right angles and form a net called a flow net. So what I've drawn below is a flow net. Impermeable boundaries are also considered flow lines, and equipotentials meet them at right angles. So you see the base is also a flow line, and those equipotential lines meet them also at right angles. Pretty simple so far. Well, we've all seen examples of these things, these flow nets. They can be generated in our seepage analyses. We don't always know what they mean, and they're always very colorful. But it's important that we have a basic understanding of what those things mean. So let's get back to our model and let's look at if we installed piezometers on the same equipotential line. What do you suppose those piezometers would all say? They're all at different elevations, but they're all on the same equipotential line. Remember, it's a line of equal energy. So in each of those, we have the same elevation of or the same pore pressure in each one of those. The water rises to the same elevation in each of those anyway. Okay, so what happens? So what happens if we have piezometers that are on different equipotential lines? You can see they're all on different equipotential lines. Well, those are going to have water that rises up to different elevations in those piezometer tubes. That's another very strong reason that you need to have more than one piezometer in any type of a geotechnical structure. It's at least a two-dimensional, if not three-dimensional problem, depending on the valley. So again, the important thing here, more than one piezometer. One piezometer doesn't tell you much of anything. So that is an introduction to flow nets. Flow nets are very useful. They have a lot of different uses. We used to draw them by hand, by choice. When I was in grad school, we had to draw them by hand so that we had a good understanding. Maybe we'll get into a little bit more about flow nets in a future video, but that's enough for now. And hope you enjoyed it. Hope you found something new. And thanks for hanging out with me.